Okay, so last class we didn't finish the last presentation. So I sent to the students all the four slides that I did it to the course. And if you didn't receive it, please contact me and I will send to you shortly. For Brazilian students, I asked Luis to put on the Lotus Drive. So if he didn't do it, ask him. So thank you, Luis, for helping me with it. And we didn't finish the last talk. And this is really interesting because of the next class will be on the junctions. So we must end the last discussion that we had on the last class. So we stopped in this slide actually. I just give a review on this because we sometimes in our group we discuss regarding magnetic effect in materials, and maybe we don't talk too much regarding the Hall effect that could be occurring during the measurements of magnetic properties. So I just review this because we already talked on last class. And the Hall effect, it occurs because of the charge deflection during the movement of the charge inside one material. When we apply a magnetic field and this charge are in motion during because of the electric field that is applied also. So we have both magnetic and electric field simultaneously. So if we have electric field, the field, depending of the polarization of the field, the motion of the charge occurs between, for instance, if we polarize the material, I will just draw like this. It's not just to sketch it. And if we polarize with this, so it means that we have minus here and plus potential there. In terms of charge, we can analyze it. I don't have another color here, but when we apply the one source, electrical source, we have positive charges. That means holes come from the source to the material. So the holes will enter the material and the electrons will move in this way to the material here. And then in terms of material, depend of the materials composition, considering that we don't have any junction here between the wire and the material. The charge will be moved inside of material, and if we increase the voltage, we will inject more charge, and if we change the polarization of the voltage, it means that the positive charge comes from here, and the negative charge comes from here. So we must understand in these terms because when we analyze the JV curves independent of the devices of the material, we must know that during the measurements, we are inducing charge in your material. So if your material are conductor, for instance, this movement will occur here, and the charge will be collected with the hole, and there is no free charge to move. And the movement of free charge depends on the resistance between this the recombination of the electron and holes. So if we have more recombination, we will increase the resistance of the film and don't have free charge. So this I will also come back on this discussion if you have some question. But in terms, when we apply magnetic field in this material, so we are also inducing charge reorganization during the measurement of that we are doing. So in terms of the magnetic field polarization, if depending of magnetic polarization, we also have some movements of the material of the charge because of the Lorentz force. So here I just draw one example, and if the current in this way, and we have a half field when we apply the magnetic field in that direction that comes out of the plane of your material. It's worth to mention that Hall effect is very useful technique and technique we can say in terms of that to measure the mobility of the carrier. So if we have more negative electrons in your material, so for instance, your semiconductor is N type, and we have more electrons because the N type means that we have more electrons, free electrons than holes. And the majority carrier is electron, the minority carrier is holes in terms of semiconductor N type. If we have a semiconductor N type, in the carrier will be deflected by this magnetic force, and we can measure the mobility of the electron that is deflected by this magnetic field in terms of Hall coefficient. So this comes from the Hall effect equation, and we can know the mobility of free charge that it has in your sample. So if you have more material that you know that there is ions, free ions, and you know that is negative or positive, it doesn't matter, but you know that has a free charge in your material, you can measure the mobility using the best way to measure the mobility is using Hall effect. And there is also several laboratory that have instruments to measure Hall effect. So we must investigate in terms of temperature, because we know that if we have high temperature, we must increase the number of free charge in your material. So we must investigate it with controlling temperature. We must investigate it in terms of the in terms of intensity of magnetic field, polarization of the electrical and magnetic field. So this is really a teeny measurement, and also gives some really nice information regarding your material and how to apply it in your devices. For instance, I don't know here in France where we can measure Hall effect, but in Brazil we are measuring in SCAR that together with Professor Marcio Daldin, and this we can measure in terms of semiconductor with light, without light, and also different perturbations. So why we must know the mobility? Because if you have a different mobility in your devices, for instance, as we design it layer by layer, different mobility will give also different charge accumulation. And in terms, if you want this charge accumulation or not, you must know how well accumulated it is, these devices, this charge in your material. I didn't get to the laser pointer. So yeah, we must know that this is tricky, and also is very important because when we also apply the materials, we usually use devices with electrical field. So for instance, if we have a photovoltaic that we must apply in the alternating current, we have a difference in the charging injection due to alternative current that is applied. So yes, we must also know that during the utilization of the device, we have this in these effects occurring during the operarization. I don't know if I pronounce it correctly, but the Hall effect occurs when we have electrical field together with magnetic field. The magnetic field also comes from electrical field, so this is quite a big, complex system. In terms of diffusion, what I started to draw here, but I didn't draw it perfectly. Diffusion will occur in your material depending of the organization. If you have a crystalline material and you have states that are free to the movement of free charges, so you can have the transport through diffusion. So we must, in terms of diffusion, know the numbers of carriers. So with this gradient here, gradient n, means number of free carriers that we have in material. If it is negative, is n, any type. If it's positive, is p type. And the carriers will have a diffusion coefficient, that is the d plus with n or p in terms of the polarization of your carrier. The diffusion, it will also depend of the materials composition, because if you have a more organized system, or you have a system that has heavy metals, for instance, the diffusion will be deflected by the interaction with the atoms in your lattice. So in terms of positive and negative diffusion, carriers positive or negative, it will also be different because the holes, they have more interaction with the lattice because of the position of the holes will be on the valence band, and the position of the electrons is on conductivity band, so they are more free, but they also have different interaction with the orbitals. If you have more orbitals in your material, if you have just sp orbitals, it's different. If you have sp df, it's quite different. So you must know how is your material organization to know the diffusion, but it's different also inside of material in terms of the position and in terms of the carriers, if the carriers are positive or negative. And in terms of diffusion, to occur diffusion, we must have a gradient of the something. So diffusion of the carriers will have a gradient of carriers. So in terms of this first figure shows one carrier accumulation here and a few carriers over the right side. And because of this distribution, we have a gradient of carriers. So to give uniformity, they have this movement. It's the same as if we apply here potassium on your material, we will induce diffusion inside of material, and this diffusion will depend of the thickness, because if it's the length will be higher, we also have more time to have uniform concentration of carriers. So this J means that we have a current without any potential being applied, just to different on the carrier potential, carrier concentration. So we can induce it during the application of potassium, but we also have it if we, for instance, just doping or just have approximation of two materials with distinct properties that we will see it on the class today. So the current, the diffusion current comes from difference in the carrier concentration. We can also measure use the Debye and Einstein relationship. And the diffusion is, as I said, is a relationship with Boltzmann because of the temperature. So we have both diffusion and mobility are one thermodynamically field inside the material. So we have this applying this concept applied in devices because of the temperature dependence of the both mobility and diffusion of carriers inside of the materials. So in terms of that, if we have one material, here is 3D material that in this figure. So we have this one, and we apply 1 voltage, and we want to measure the current that is getting in the material and is getting out of material. So how we know that we know that if I introduce one current, I will receive one current out. We usually do it using multimeter. So if you are in the lab and you know if there is any continuity in your material, we just grab the multimeter and then you put it on the voltage and put on the there is the continuity on your multimeter, and you just with two points you can just put on your sample, and you can hear it if it is continuous or not. If it is continuous, it means that will be you can hear one beep. If it's not continuous, you will not hear anything. But what you are doing using the multimeter and you hear the sign, you are applying one voltage, exactly one voltage with multiple multimeter. And if the signal is collected by through these 2 points, it means that the current is crossing of a device, of a material that you are measuring. If this material has too high resistance, and you put 2 points, you will not hear anything. So it means that isolated material. So the resistance is too high and the current will not cross your material. Generally, we do it to see, but we must be careful, because if you put 2 points and you put 2 points like this and like this, is different, because if you increase the distance, you must have a higher resistance. So if you want to just have a quick comparison to know if your material is more conductive, there is more conductivity than another material or another treatment, you can just use your multimeter and measure it. You are doing this in terms of quantum physics. You are applying one carrier here using your multimeter, so it's giving one, for instance, electron. And if you have just perfect material with a perfect conductivity, is a conductor material with free states to your electron. So this electron here, I don't know if the guys in the online can see, but the dot, red dot over the orbital, the conductivity orbital here, energy of conductivity orbital. This is electron. So if you have just free states and your material is conductor, so the movement of this head dot will be freely move over all your free states. It means that the head dot, if this would be dynamic, he would move in terms of EC, that means energy of conductivity bond. So the movement here means that the electron is free in your material, and you have more free more conductivity properties. But this is not what usually happens. What can be occurring is when you inject electron here with in the X, the electron can also recombine with the hole. This hole comes from the trap, oxidation, something that you have in your material and that you cannot control it. And this can also recombine and can also be created inside of your material because you are using current. It's quite interesting, but you must think that when you applied one potential, you are giving kinetic energy to the electron. So sometimes you can give too high energy to the electron, so the electron goes to your material and also can ionize or gives just energy sufficient energy in terms of you can just move him to another orbital. So this is also things that can be occurring. And in terms of one distance with thickness, dx thickness, we will have a Jx current in and Jx plus dx current out. And if we have a Wissem in and Wissem out, this means that we have a perfect conductor. But in general, we decrease the current that we are applying. So this means that we are having a recombination or generation of charges. And we can also know it in terms of length of a recombination of your electron or hole in terms of carriers. If you have, it's quite hard to have just a free electron and not be trapped. So we can measure the length of transporting of electron or hole diffusion inside of material, knowing the diffusion and the time life of your diffusion carrier, that both of them will also depend on the material's properties. So to know if how thick we can have, to don't have a recombination or to don't have any creation of the charge, just the transportation, we must know also the length of recombination carrier of your material. This I just started because I didn't finish properly on the last class. We didn't have time to discuss it. So today's class, we will analyze it, but we will analyze it in terms what happened if I have two different materials. So everything that we discussed, we just discussed it in terms of one material, isolated material, but in real life, we don't have, we cannot have just one isolated material because sometimes the material is over one substrate or the material needs one contact, or we must have two materials to have better performance because of the application. And today's we will discuss in what happens if we have two materials together, and everything that we discussed in the third class we will be talking in the fourth class. So here we will understand what happened during the contact of two material, and we will start analyzing semiconductors with p-en doping. When they come together, what happened? So we know that the junction is the term that we have when we junction to we have a junction of two materials. It doesn't need to have two materials, two semiconductors materials. We can also have a junction, for instance, metal and semiconductor material. We can also have semiconductor, and semiconductor with isolating material, but in terms of isolating properties depend because of if the material, the thickness of isolator material, it will affect on the charge transport, but we can also have isolator, conductor, and semiconductor. So we must know that in terms of electrical properties, everything that we junk, we have different carriers though. So the carriers will move to the side that has lower energy. So this movement we will analyze and how we can manage this movement to have one perfect device. So during when I did this fourth class, I read one phrase that it impacted me, because sometimes we seek for new materials. We seek a lot for new materials, and we didn't we didn't analyze the material correctly. Sometimes we don't need to change the material. We must need to analyze the junction of material. So in terms of efficiency, we can the phrase that I saw was a higher efficiency do not comes from new material, but comes from new engineering of interfaces. So we must understand the junction to understand the efficiency. So the motivation of this fourth class, that maybe I will continue on the next class because of the time. We just have 1.5 hours. But I will start with p-n junctions. So why p-n junctions matter? So in terms of semiconductor devices, is the foundation of every semiconductor devices, transistor, diodes. Diodes means also LED or PV, and it is the foundation of the new devices, and we can also control the charge transport using these p-n junctions. So we will see how we can manage the charge transport, how we can increase the transportation or decrease this transportation just with contacts. in terms of interfaces, we will see equilibrium and non-equilibrium. It means that equilibrium, when we have the diffusion also already diffused, but the diffusion already occurred, and the non-equilibrium during the diffusion. And the p-n junction is not just a device, is that everything that rule the devices. And it's the p-n junction is a thermodynamic system driven out of equilibrium. So we'll start understanding what happens during the formation of the p-n junction. So we will review what is happening before the junction, so the isolated p-type and n-type material. So it's worth to mention that we have one semiconductor with two different doping. So in terms, if you remind in the last class, n-type, for instance, silicon with phosphorus dopant, and the p-type was silicon with boron dopant. So we have the same semiconductor with two different doping. So it's different if you have two different semiconductor, because sometimes we have it on our research, but for now we just analyzing two semiconductors with two same semiconductor with different dopings. So in terms of n-type, the majority carriers are electrons. So reminding the Fermi level of electron will be, this is just one draw of the overview, is not the density of state, as I talked earlier, because density of state will depend of the key space in our material. So you know that we can represent the material overall with this sketch here, but it's not a physical sketch. It's just one didactic sketch. But in terms of energy firm, we will have the energy firm close to the conduction band in n-type semiconductor, and if we have the p-type semiconductor, we have an energy firm level close to valence bond. And the isolated materials, they are in equilibrium, but if they are isolated, not when they are with each other. So what happens when we put two materials together? So the p and n-type together, we have this movement comes from diffusion. So in the contact, there is a huge carrier concentration gradient. So the free charge will move to the less potential charge. So in terms of if we have p-n junction, the electrons comes from the n is blue, so he is moving to one region here that we will see what is this region later, and the plus charge will be moved to the region of this region also, because there is low energy for the plus charge in this region. So if you see here this yellowish comes close to the charge, it means that electrons and holes are recombining. So when they recombine, they emit light. So sometimes it's quite common. My students just measure, for instance, JV in material and see, oh, it's brightish because you are recombining holes and electrons in your material. And it also comes from the junction, because there is no any voltage applying. It's just the contact with two material with different dopings. So the light comes, if you see it microscopically, so we call, so the electrons diffuse from the N type material to the P type material, because in terms of Coulombic attraction, the positive will attract the negative, and as in the N material has more negative charge, the pull the electron to the N side, to the P side from the N side, and the whole will also diffuse from the P type to the N type. It will be in different directions. So, for instance, the electron comes this way and the holes come this way. There is one region between them that we call space charge region, or depletion layer. It means that we have one non-equilibrium movement, but sometimes it will be one equilibrium, and the disequilibrium will generate a space charge deflection of the bands. So in terms of the contact, the diffusion current starts immediately. If you could measure during the contact of the materials, you will measure one current just to come to the diffusion. Okay, so after the diffusion, so the movements of the electrons in holes on one side and another side, we have a fixed ionized donors plus on N side. So what means that after the diffusion, in terms of Coulombic attraction, is better to the holes be close to the electrons, comes from the N type, then close to the P type. So this is why in the deflection region there is a different polarization. So you must know that we have this is called space charge, because in terms of movement, the space charge will attract the free electrons from the N type, but the space charge from the electrons, free electrons, space charge electrons will block the free electrons from the N type. So it's quite interesting, this movement. And you must know that there is this distinguishing polarization after the diffusion. So in terms of holes, we have holes in the region close to the N type, and we will have electrons close to the P type. So after the diffusion, we will not have mobile carriers anymore, just during the contact. And yeah, the most interesting thing that happens is actually it's two interesting things. Is the space charge region, that this difference in the polarization when we have this contact, and also the building electrical field, because this building electrical field means that I have intrinsic voltage just because two materials with two different doping are linked, so they are junted. So this will rise one building electrical field. So in terms, I just give you information that I think everyone knows, but in terms of diode, this building will give the movement of electrons and holes that are created from the light. So in terms of photovoltaic effect, the voltage from the photovoltaic comes from this built-in electrical field. So if you want more open circuit voltage, you must change the building effect. But I will return it on the photovoltaic class. That is I think the 6th class, 60 class. Yeah, so the building electrical field is quite nice because it means that you have one internal field that can move the charge or can block the charge. So this is why the diodes can transport in one direction or in block in another direction. The field is self-consistent, so it means that the field it created without any electrical field come out from the material. It's just from the material properties, and it arises from the diffusion itself. So in terms of current, we can have two kinds of current created inside of junction. So we call it diffusion junction, diffusion current that comes from the contact. So they have this movement of charge, but we also have the drift current that comes from building electrical field. So in terms of contact, PN contact, but also in the metal and semiconductor contacts, we have these two kinds of current, that is the diffusion and drift current. And during the equilibrium, which means that in terms of this figure, we have both drift and the diffusion. They are the sum of the drift and diffusion are net zero. So is electrostatic system well balanced itself, and just to remind, during at the junction we have this spatial charge, that means we'll give one equilibrium of diffusion and drift. Okay, so we know that during the contact we have this diffusion, and then we to arise one drift current that opposite to the diffusion. And in terms of energy diagram, what happens with the diagrams of the materials. So before the contact, we have the valence bond, the energy balance, and the conduction bond here, as we are analyzing two semiconductors with two same properties, just the doping. So we just have this movement in the Fermi level. What happens when we put they both together? So in terms of devices physics, the devices of interfaces, the Fermi level will be the parameter to set all the layers. So if you have, for instance, here metals and things and another junction, everything that will comes will be aligned in terms of Fermi level. So here, the Fermi level in this and this position. So what will occur because of the diffusion will decrease the energy of valence and increase the energy of valence of the p-type, decrease the n-type, increase the p-type. So we have this movement of energy levels, and the alignment of Fermi will be on that. And this difference in the energy of the materials, because before we had this energy, and after the contact we have this two energy of the materials, and both of them are distinguished by one amount of energy, and this amount of energy is key VO, so the building electrical field. So it we can see that has this deflection in the band. So the deflection means that this deflection between those two bands here, and this deflection is the region where we have the free charge, spatial charge, actually, not free charge, sorry, where we have a different polarization in terms of when we compare to the semiconductor itself. So when we analyze the electrostatic potential here, you can see there is this difference in the voltage comes from the difference in the doping of the two materials. What is quite important to mention, depending on the level of the doping, this deflection will be higher or lower. We also have one length of the deflection that here in this figure we can see with the double V, in this length will be ruled in terms of the doping of the materials. So analyzing the whole diffusion and the whole drift. So in terms of if we have the N-type there on the right and the P-type on the left, the whole diffusion will be to the right and the whole drift will be on the left. And the opposite comes from the electron. The electron diffusion will be on the both sides to the current, and in the whole electron diffusion will be on the left because of the N-type is there, and the electron drift will be on the right. In terms of the current here, because of the current, we analyzed the movement of the positive charge, so it's opposite to the movement of the electron, just to know if in terms of physics or in terms of engineering, but the movement of the current is opposite of the movement of the electron. So this building that arises from different energy levels and coming from different on the doping. As I said, if we have a higher doping, we also have a larger building field. If we have a higher temperature, it will also modifies the carrier statistics. So if we change the carriers, the number of carrier, we will modify the doping, also the material. So the thermodynamic, there is a thermodynamic effect. So in terms of the same temperature, we can compare, but if we have a different temperature, we cannot compare the material. So in terms the building potential, in terms of physical meaning, what is the voltage necessary to conceal this deflection in the bond to do a flat bond? So it means that we are applying positive charge in one direction and negative charge in other direction, and we will have this movement in the bond. So the energy necessary to have flat bond is the voltage built-in potential, and it will and it is the voltage necessary to conceal the diffusion of materials. And as you can see here, we can also predict in terms, if we know the temperature, we know the number of dopings, and this N acceptor and donor, it means N P-type, and the minority is the N minus, and if we have this information, we could predict the voltage, but it is worth to mention this physical interpretation is different if we have different materials. So sometimes we don't see this trend, for instance. So this is also one thing to do in research, in this one field of research, to analyze how 2D materials, for instance, or organic materials, or perovskite materials, they are what's the behavior of these materials applied as in the junction. So it is one field of research inside physical devices. So what happens with electric field profile when we have this junction? So as we saw, we have this movement in the junction, and this movement will bring the the p-type will have the electrons and have the holes close to the n-type. Here I didn't say, but here is more specific. The numbers of the electrons and the holes are the same, but you can see that the length of the region is different because of the mass, effective mass of the holes and electrons. As holes has higher effective mass than the electrons, so the region of depletion will be lower than the region of depletion of electrons. So this will also affect in the electrical field distribution. So in terms of the, I'll just close the term. So in terms of the charge density, here is one graphic, the B, is the graphic of charge density. We have, in terms of distribution, in terms of distribution of the position of the film. So we have more charges, the density is more of the plus charge, the host charge, and the distribution of the electrons is large in X and has this lower density if we are analyzing in one direction. And in terms of electrical field, we have this distribution that comes from the derivation of the charge distribution. Here I just put the equations, but I have also one book where we open all these relationships. It's not because of the time I will not show it here, but I will send. Actually, I sent, but I didn't send my book that I just opened the questions. I can also send to guys the book that I'm writing. So writing. I didn't finish. So in terms of electrical field, we have this difference in the position, and we have the highest electrical field in the metallurgical junction. The metallurgical junction means that is the point where we have in terms of space, the exactly point of the junction. So we have this linear distribution of the field, the electrical field, but in opposite direction because of the difference in the charge. And the field has this triangular shape, and the potential is quadratic. And also quadratic, but in terms of density is different if we are analyzing holes and electrons. And also the triangular shape is not symmetric, is asymmetric because of the charge density difference. Okay, I think I saw it. In terms how we can know the depletion with so as we discussed it, it will be different if we have distinct dopings. So to know the width for, in this case, is silicon N-type, P-type, or also apply the arsenate gallium, arsenide gallium. So it is the traditional semiconductors. We can apply it in terms of the dopings. For instance, organic materials, we cannot use it because we don't dope the organics, the traditional organics, the polyaniline, for instance, the guys that we use on pony, we can dope it, but PDOT also, we can also dope it. But in terms of P3HT or PCBN, PTBTH, PTBTH, we don't have any doping. We just have difference on the charge distribution, but we will analyze it later. In terms of materials that we know that have free charges, so if it's true the materials are organic with free charge, so we can apply it quite close, we can apply, but this works perfectly for common inorganic semiconductors materials, silicon-based, and some leagues that is already established and is already commercial in the transistors and diodes that we have already in our devices. So the depletion width we can know through this. So also here we have this dielectric constant appearing. So it will be different if you have material with high dielectric constant. So this is the reason that we have different relationship with we change the materials, the new materials is different for the traditional materials. I don't remember why I did this. Let me think about it. Yeah, but this I think I just put to review that. The next is the okay. When we apply electrical field that comes out of the materials junction, so we also inducing difference in the energy levels of the materials that are in the junction. What I want to say with it, we have isolated materials. When they are put together, we have this drift diffusion of the charges. When we catch this junction and we apply voltage in this junction, we are inducing charges depending of the polarization of your bias, and this polarization will gives different in energy alignment. So, for instance, depending of the electrical field that you apply, we can, for instance, if you have the electrical field comes from this side, we are introducing electrons in the end, holes in the end here, and electrons in the p type. I'll just give it a side-by-side explanation depending of the electrical polarization that you are applying. So, for instance, if we have a forward bias, so what happens with the potential depletion width and also the deflection that in the bands. So as we saw here, during the junction, we have this difference in the voltage. So the VO here without key, but we are multiplying with charge, also elementary charge. But we have this building potential. If we are applying forward bias, it means that here, I don't know if the guys online can see, but if you see in terms of polarization, just see this in the drop there. This means positive, this means negative potential. So if you see in forward bias, you have a positive on your left and negative, then comes out another positive and negative. That means we have a combination of two electrical source. But here, what means is that the holes come from electrical source and are applied the potential is positive and the potential here is negative. So means that we are actually, I drafted here wrong. Sorry, this is negative. Sorry guys, this is negative and this is positive. Because this is the potential, the charge will be repelled. So if this is potential plus, it means that the charge, actually, no. Let me see here. No, it's right. It's right. It's positive. Sorry. It's right. It's negative. I just move to the another here. Don't be confused. But what I said earlier is correct. What I want to say is, if we have this potential here, so it means that the negative potential and positive potential will pull the electrons here, and here is the N. Here is the B type. So forward bias means that we are applying one bias that is it will inject positive charges in the p-type and negative charges in the n-type. This is why it's forward, because we are inducing direct charges to the direct materials. So the n-type has free electrons, and p-type has hole as majority carrier. So in terms of charge distribution, what happens here? Here we are having the energy Fermi level. So if we are inducing more electrons, the energy Fermi level will be going up. So it means that we are creating more carriers inside of the materials, and these carriers is the same carriers of the material. So if you analyze the energy Fermi, you can see the 30 draft here. The energy Fermi is going up, and the energy Fermi of the p-type is going down. Actually, it should be a bit down, but it's not too much down because of the effectivity mass here. And what happens with this difference between the deflection band? So if you saw here, if you see in the diagram, before the voltage, we have here, and we have this deflection here. Also, the deflection is different in the balance and the conduction band. This is just one dielectric draft, but because of the effectivity mass is different to the deflection. And if you put more charge, negative charge, this comes here, and this will come lower, but not higher as the n, is not symmetric, but will have this difference, and there is one inside the deflection that will reduce this potential, built-in potential. So you can see it in terms of length of the potential. That is the second the difference between the position of the here. The difference lower is quite like this. So it means that this difference here, that we call key V0 minus V of forward bias. This difference here, this V0 is building potential, and this V forward is the voltage of electrical field coming out of the material that we are getting from the source, from the potential stat, for instance. So this is the bias coming from the source, and this is the built-in bias, built-in electrical field. So depending of the voltage that we are applying, you can see that sometimes we can also have this flat band condition. So sometimes we apply voltage and it suddenly increased the current, and I have my material better. No, you just have the energy sufficient energy to reduce this built-in effect also. So in terms of the particle flow, as we are applying in the same direction, one thing that I didn't said, and is quite important, is if we have this semiconductor here, N-type, and we have this P-type semiconductor, and the energy Fermi here, actually the N-type is here. P-type. This deflection band here appeared, and the movement of the electrons is better to the electrons come from to the lower potential. If you have an electron here, for instance, the movement of the electron will be in this way, and the movement of the holes will be on this way. Even that if there is any difference in the charge space distribution here in the interface, the lowest movement of the charge will be in this direction. So in terms of the whole diffusion, the whole drift, not diffusion, will be on the left side, and the electron drift will be on the right side. So this is the drift, is not the diffusion, it's different. So it will be opposite direction of the charges, free charges of the materials. So yeah, we can also okay. So in terms of when we apply a positive voltage to the P side, it means that it's forward bias. So we reduce the barrier. So this barrier here reduce. That is the difference between the energies level. If we reduce the barrier, also the depletion region, that is the width, W, the width of the depletion will be narrow. So if we have too narrow region, we also can tunneling the charge through this depletion. But in terms of the depletion will be reduced, and if we apply sufficient charge, we will give a flat band condition. And carrier injection also occurs because we are applying voltage, and the movement of electrons will be depending on the potential. Sometimes we can have this movement because of the direction. We will reach flat band, and then the conduction comes. And this transport we call injection-driven transport because we are modifying our material using our measurement. So we must understand that the electrons comes from our voltage also will interfere in the movement of the diagram, energy diagram. I will return on the reverse bias, just continue on the forward. This is another draft that I put just to if there is some questions, but you can see here what I showed is the depletion width is low, is sharp, and also the difference between the conduction band of the two materials will be flat depending of the potential that we are applying. In this case, there is also one difference in the potential, but sometimes we can apply a potential that could have a flat band condition. So here, in terms of the carriers, we can analyze it. We are applying positive carriers in the positive region here. So we are applying positive charge in the majority positive charges, and we are applying negative charge in the majority negative charge of the material. But what happens with minority carriers? Minority carriers are the carrier that is not the main carrier here. So the N type, we have the majority is electron, and the positive, the P type, the majority is holes, are holes. So the minority, in this case, so the majors and minors. Here are the electrons and the holes. So the movement in terms of electrons will be ruled, the current of this condition will be ruled through the movement of minors. So you can see it. The minors will have this movement in terms of current. The positive charge will go to the P type, and negative charge will go to the N type. So it means that in the PN junction, when we apply voltage, the carriers that are responsible for the current are the minor carriers, and are not the major carriers. This is the condition. If we are having these materials in the dark, and without any abruptal temperature difference in temperature, because if we have light, for instance, so it will give different charger carriers density, but in condition that we are analyzing in dark and without high temperature, we have the current ruled through minors carriers. So in terms of this, we can also know the diffusion length of these minors that could be also in terms of Boltzmann relationship, Einstein diffusion action with Boltzmann, but the diffusion is related to the quadratic length and diffusion coefficient and the time life of the minors. So this this will give emphasis on recombinations physics that can be occurring if we have, for instance, one length that's too high enough to have recombination instead of transport, or if we have some trap that could reduce the length of the diffusion and also will give a recombination more probability to combination than to transport. Okay, we analyzed the forward bias and what happens if we have a reverse bias. So it's the same consideration, just what we have is the reverse. We will modify this polarization here. If we modify, it means that we inject negative charge from your source to your material, and there will come negative charge to the P side and positive charge to the N side here. So negative charge to the P side, what will interfere in terms of energy level? I will not draw it again, but in terms of P, and if we have this alignment here, that is the equilibrium, and we inject more electrons in the P side and more holes in the N side, you can see that the energy Fermi will increase on the P side and will decrease on the N side. And the difference between the P and N side will be increased. So this improvement will give give more. We will need more energy to the free charges that are the minors, going to his direction. So if we needed more energy to come, it will block the transport, because if we are, you can think in terms of stairs. If you have some huge stair to decrease, you are you need more, you are more afraid to go. And in terms of electrons and holes, we can think regarding it, because if we have more steps to go, is easy to go, then we have a huge step. Sometimes we are afraid to go in this direction, and the condition will also give this property, and the movement of the electrical field uh, uh, you can see that has higher energy potential than before the equilibrium. Before I talked regarding this diode equation, I just give this information regarding the movement of the electron drift. If you see here the holes coming from this side, as this step is higher, so it will be lower amount of the current than the diffusion current than in the case of the forward and the equilibrium bias, equilibrium condition. So if you see this set here is lower because of this barrier here is getting higher, and it will give some difficult to the movement of electrons. In terms of the diode equation, we can also fit the current in terms of potential. So we have, if we have forward bias or reverse bias, we will have a block current and a transport current, and these transportation are ruled through exponential equation, and there is a relationship with temperature. And in terms of this fit, we can see that this iode condition will depend on the diffusion of the properties of the material, of the we also depend because of the transport itself, the length of the charge prior to recombination. So this is the length of the charge inside the material, that the charge could be moved inside the material without any kind of recombination. And the number of doping as of the acceptor and donor, or and in P type that we are seeing here. And the drift, the diffusion length, and what is quite interesting, that when we see that, I don't know if I put here, but when we see here the JV curve in the reverse forward bias, so in the forward we can have this transport, and in reverse we will not have this transport. Instead, one breakdown here that we will talk more about this breakdown. But the diode polarization comes from this, and the current that we have here, that ideal diode equation, the movement of this current is just through minority carriers. It's not through the majority carriers that we have in the material. Even that, the movement is different if we have different doping, but the transport will be ruled through minority carriers. So this is why we can use two semiconductor with different dopings to polarize the electrical current. So it means that we just can't transport current in the forward bias. We don't have transportation in the reverse bias. And this is quite interesting because after one amount of energy, of potential, that in silicon, for instance, is 0.7 voltage, in germanium is 0.3 voltage. After it, we have abruptal current, and this abruptal current comes from the minorities and also the built-in potential that getting flat condition and allowing the minorities to be freely moving, and also the electric field pushing and pulling, depending of the charge that we are analyzing, but we have several physical interpretation inside of the material that could increase the current of the devices. So this is why we don't have a linear relationship as ohmic and resistors, but we have exponential transport in terms of voltage. And this is quite interesting because we can have a fast transport and we can also block the transport of something that we don't want. In terms of the reverse, here, this example, this example, we have this different in the red line here. You can see that has some not hysteresis, but it's not well flattened there because it's common to see like this in real diode. It should be flat in zero, but we have this difference because of the traps, and these traps also can transport. In this we will also discuss it later. And in terms of reverse bias, we don't transport minorities, we don't transport majorities also, but sometimes we can see this transportation coming from the traps. And if you apply a huge potential, you can break the material with different kind of breakings, but you can break material in terms that you can have this transportation, and if you do again measurement, you will never see your material behavior anymore like diode. So you have a breakthrough of the voltage in terms of the silicon. This in a perfect silicon, monocrystalline silicon, we have this breaking on 50 voltage, but depending of material, you have this lower, and this is you must be aware of. Uh, we can also analyze the JV curves. This is IV curve. JV is just in terms of density of current, but the IV is the current. But we also can analyze the current semi-logarithmic, right? It means that we have this format in diodes, and the transport should be different when we analyze the position and on the current. This example here is one organic material. When we apply, we just do dark measurement. So we must have a lower current in one side and higher current in another side. It means that we are blocking one carriers, and we are transporting another carrier in another side. And when we put light on it, you can see in terms of the intensity of light that comes from the brown to the green, increasing the intensity of light, we will have more free charge, and the current will significantly be increased in the blocking directions. But this, in terms of photocurrent in diode, we will analyze it also later. Just one example that in terms of IV curve, we can analyze it in semi-logarithmic format. And the additivity factor, which means that diode equation, we could fit it using the equation, but if we have we want just to fit our diode, we could use it and see if we have the n close to 1 or 2. This would be good for Rafa, João, that are analyzing, even that is just the JV curve. If you have the one, it could be your material has diffusion dominated, and if you have two and two, you have more recombination being dominated. So it's not just I put it as solar cell analysis, but also for semiconductors and interactions of semiconductor with another material. And if you want to analyze it, your JV curves behaviors. It's quite interesting to analyze the junction this partial charge will give one intrinsic potential depending of the number of doping and the properties of your materials. But also your junction will rises one intrinsic capacitance. In this capacitance could be depending of the materials, but could affect the measurement that you are doing. So in terms capacitance can the junction can avoid the trap, but also can can storage the energy, and when you do the forward bias, for instance, you free this storage energy that you did on your junction. It's not that your material is bad, but you must be aware of it, and you must know that different material has different capacitance also. If you have more materials with more sites, free sites that you can put some electron and keep it trapped, sometimes this electron also can move, and this movement also will affect the measurement that you are doing. And we can also know the capacitance of the interface, analyzing the bandwidth and the dielectric property of material. The dielectric property of material we can know using ellipsometry measurements or something that is the relationship between materials, but yeah, you can it's just one thing that during the interfaces of materials you must be aware that depending of material that you use, and even the perfect crystalline material, they have capacitance properties of the junction. And this is not bad, but we can also apply it with our objective, our goal that we want to improve in devices. But use it, for instance, in variators, actuators, or some things that are capacitance dependent. Also, batteries or supercapacitors, we can also know in terms of it. And doping profiling, I didn't know I updated it. Yeah, we saw in this JV IV curves that in terms of a reverse bias, we have this breakdown in the transport. That means in terms of the one potential, reverse potential, we could transport, even that should be blocking. And this transport can be ruled to two kind of breakdown. We call it Zener breakdown and also avalanche breakdown. I don't see how to say it in English, but it should be avalanche. Zener breakdown comes from if you have too high doping material and the difference in the doping is quite huge in terms that you will have tunneling, so you will not block your miners to be transported, but the miners will be tunneling through this barrier. So yes, if you have high doping and you can also have this effect occurring. When we should block the transport, the material are tunnel, the carriers are tunneling through the potential barrier here. So we have this transport here because of the huge doping. So yes, you think if we have doping, high conductivity material, so it should be better. No, sometimes it's not so good. You must know that depending of material and the contact that you are doing with another material, and if you want to block, but of course, if you don't have a huge potential, use being used, you also could use it, but in terms of profile of IV curves, you can see that exponential in forward bias and in reverse, sometimes block, and then tunneling, and the transport is also high. So this is what I think that could be generating in electrochemicals measurements, for instance, of our material in laboratories. And yeah, you must be aware, because you give more free charges that could also impact in your material in forms that you are analyzing. And this voltage is low. So this breakdown voltage is low. If this breakdown is low, it could be considered Zener breakdown. Avalanche is also one breakdown that could be occur in materials and also in electrochemical measurements, because we have redox things doing, but what is happening when we have avalanche mechanism? We are injecting carrier with your electrical field with high energy that could ionizate the materials and increase the carriers, but different from the Zener, it will just arise from higher voltage, because it will need higher energy or the energy necessary to ionizate your material. So to distinguish these two kind of breakdown mechanism, it should be Zener low breakdown voltage and avalanche higher breakdown voltage. So yeah, in terms of figure, I just put here, this is light green here, is electrons come from your bias here, and you ionizate your material. Here's the lattice of material with atoms, and depending of the energy of your atom, you can ionizate deep electrons. You don't know. I know that some electrons could not be, because the electron field that we usually use in low voltage in laboratories, low voltage is less than 10 voltage. But when we apply it in the engineering devices, for instance, applying in buildings and other things, we must know that this could come from the high voltage. Same voltage, for instance, could impact in these performances. So the next would be PN junction under illumination. I don't have time to talk it right now, so I'll give you this talk on the next weeks. So just to remind, the next week we will not have the class because we are in the vacation here. So we will back on the second week of March. So see you there. Bye bye, guys.